Okay, now we continue with laminar flow in pipes. Now we have the same assumptions as we had made with Darcy-Weisbach derivation, which were constant diameter, incompressible fluid, fully developed steady flow that we have. Now, we also concluded with the derivations that we made they're applicable to laminar and turbulent flows simultaneously. So what we have is now going back to 272, the first chapter where we discussed viscosity concept, we derived this equation, Newton's viscosity law, which says shear stress to be equal to mu times del U over del Y. Now, the way that we define that del U over del Y, if you remember, from the boundary, we take that vertical Y axis. Now, here, as you see, I have R, which is defined from the center line of the pipe to the wall that we have. Let me just go back. And as you see, R is from center line and it goes to the wall of the pipe, whereas Y is defined as from the wall to the center, either from this side or from for every cross section of every section, for circular section, from each point, I should say. So you have Y from the wall to the center, whereas R from center to the wall. So they are pointing opposite directions. So if I would like to express this in terms of del U over del R, as Y and R shows two opposite directions, so we will introduce a negative minus to the equation. So shear stress will be equal to minus mu del U over del R. So mu's will cancel each other. I will obtain del U over del R to be equal to minus shear divided by mu. Now, if you just remember, we just derived shear stress to be equal to gamma HL 2L times R. Now, as del U over del R is equal to minus shear divided by mu, all we do is we take this shear and divide it by mu. Then, with this R that I have, now I will be looking at the change of U with respect to R. So if you just write del U to be equal to, this is the constant term that I have, R times dr, and we put those integrations. So if you just take this very simple integral that we have, du integral will be nothing but u. This is the constant that I have. Integral of r dr will be equal to r squared divided by 2 plus the constant of integration. So that is the result from this integral that we can solve. Then I can write r to be equal to d over 2. So radius when r is equal to d over 2, so it is, I'm at the wall. What happens is the velocity at the wall will be equal to 0. This is due to that no slip boundary condition. Again, the things that we had discussed in the first chapter of 272. So when r is equal to half of the diameter, when r is equal to the radius, then u will be equal to 0. So from here, if you take u to be equal to 0 minus gamma HL for L mu, for r, I will write d over 2 squared plus C1. From here, if you just solve for C1, you can obtain that it is equal to that. Then I can just substitute it in this equation to solve u as a function of r. This times 1 minus, coming from here, 2r divided by the diameter square. So this is just from that simple integral that we can solve. Now, when r is equal to 0, what I mean by r is equal to 0 is I'm at the center line, the velocity will be equal to the maximum velocity at that point. So u is equal to u max. And when you put R is equal to 0 here, that U max will nothing be equal to that term. Sorry. So U max is equal to specific weight, head loss, D squared divided by 16L mu. And again, if you just use U max as this, so I can write UR is equal to U max, which is nothing but this term, times 1 minus R over capital R square. Here what I had done is for D, I had written 2 times capital R, so 2's cancel each other, so we end up with R divided by capital R square. In fact, you should be familiar with this relation. We make use of this kind of velocity profiles a lot to calculate the discharge passing through the system. So this U max value is defined to us, if you remember, and I can use it. I can use this velocity distribution given as a function of radius to calculate the discharge passing through that section. Now, before continuing with the discharge, if you look at that UR, U max times 1 minus R divided by capital R square. So when R is equal to 0, U will be equal to U max. Going back to this at the center, I'm going to have maximum velocity. Here we had showing as U max. At the walls, we have no slip boundary condition, so it is equal to 0 there. Now, the discharge is calculated as integral for the whole area U dA. And for U, you can just simply write this. dA will be written in terms of radius, and of course it will be equal to 2 pi r dr. And if you just take this integral, which we had taken a lot in 272, you can obtain that discharge is equal to this. Pi capital R square U max divided by 2. And for U max, if you just substitute these values by making necessary cancellation, you can obtain that discharge is equal to this value, which is obtained from the integral that we had just solved. So the average velocity by definition is nothing but the total discharge divided by the cross-sectional area. What was discharge? Pi r square U max divided by 2 divided by area, which is pi r square. They will cancel each other and we end up with velocity being half of the average velocity, I should say, average velocity to be equal to half of the maximum velocity at the center line. So here, that V, average velocity, will nothing but half of this maximum value. So in the calculation of discharge, either we use this parabolic distribution that we end up with for laminar flows only. Be careful with this derivation. This is the condition which is valid only for laminar flows. So if you remember the discussion in 272, this relation is only valid for laminar flows. Hence, the derivation that we had made is only valid for laminar flow, and you end up with having a parabolic velocity distribution where the average velocity is half of the maximum velocity that we have. And tau wall is minus mu del U over del R from this relation. And when R is equal to R, that is, tau is minus mu del U over del R. When R is equal to capital R, we know that that shear stress is named as wall shear stress. So wall shear is calculated by that. And if you take del U over del Y, del U over del R from this relation, you can obtain that it is equal to 2 pi U max divided by R. So for U max, if you just write 2 times average velocity and rearrange this equation, wall shear stress becomes 8 mu average velocity divided by D that we have. Okay, head loss, we obtain head loss as 4 times L gamma D tau wall. in the previous derivations. Now for this tau wall, I replace this relation 8 mu velocity divided by d, make the necessary cancellation. We obtain head loss to be equal to 32L dynamic viscosity times average velocity divided by specific weight d square. Now, keep this relation of head loss in mind. Now I will be writing Darcy-Weisbach equation again, which we know at this point is F L over dv squared divided by 2g is the head loss that we have. Now, this head loss is equal to that 32L mu v divided by gamma d square. I will write it that way. And with this, I will just play with them a little bit. So I have gamma, I have a velocity term, and just if you just play with them a little bit, for example, for v, I will try to obtain d squared divided by 2g. I will write gamma as density times gravitational acceleration, so that here, as you see, we have v squared divided by 2g term. We multiply both sides by 2. And what else we had done is I obtained density, velocity, d, and here I have dynamic viscosity. This term is nothing but Reynolds number that we have. So with these, I ended up, they're all equal to each other. We had just multiplied and divided by several terms, and we had written just then a specific way to be equal to density times g. That is the whole thing that we had done so far. And we just rearrange this equation, and we obtain that 64 divided by Reynolds number times L over D is equal to V squared divided by 2G. Now, we had started with head loss to be equal to this 32L mu V divided by gamma D squared. That is the relation. And with playing with that relation a little bit, I ended up with this. So now, if we compare this with the Darcy-Weisbach equation, I have F, instead of F, I have 64 divided by Reynolds. I have L over D, V squared divided by 2G. So which we can conclude that F, which we had derived to be function of Reynolds and epsilon over D ratio, Reynolds number and relative roughness, which we concluded for laminar flow to be equal to 64 divided by Reynolds number only. So this means what? If you know that you have laminar flow in your pipeline, how do I understand whether I have laminar flow or not? Simply by looking at the Reynolds number. Reynolds number is calculated as average velocity times diameter divided by kinematic viscosity, or average velocity d times density divided by dynamic viscosity. It's all the same. So if your Reynolds number becomes less or equal to 2000, then I know that I have laminar flow in my pipe. If you have laminar flow in your pipe, then you can directly calculate your friction factor to be equal to 64 divided by that Reynolds number. Even though in our derivations we had made we obtained that, we derived that friction factor is function of Reynolds number and relative roughness. Relative roughness is epsilon divided by diameter. Even though we know that we concluded that F is function of Reynolds number and relative roughness, we see that if you were to have laminar flow in your pipeline, then your F becomes to be equal to 64 divided by Reynolds number. That is the magnitude of F that you can directly calculate. So dependency on epsilon over D, dependency on relative roughness drops for laminar flow condition. So what we will do in these pipe flows, as the difference from 272 is that we will calculate the friction and minor losses in the system, and we use Darcy-Weisbach equation in the calculation of friction loss, I will be in need of this friction factor value. So if you have laminar flow in your pipeline, that F will simply be equal to 64 divided by Reynolds number. And from this relation, you can just calculate your F, substitute it in the Darcy-Weisbach to solve for your friction loss. Then you can use it in your energy equation to calculate the unknown things that you are looking for. So if we just go over our notes for 272 laminar flowing pipes with the same assumptions that we had made. What we had started with Newton's law of viscosity, we know that this is only valid for laminar flow relation. We said very small, very slow flow motion, and we write it in terms of R. That's why we put that negative there. We relate del U over del R to minus mu divided by shear stress from this relation. And what I end up with is shear stress and that relation. We solve for our integral. We put the limits to solve for the constant of integration, and I obtain UR as a function of R, and all these terms had loss, specific weight L and mu. And we again use R to be at the center where U is U max, and we obtain the parabolic velocity distribution for laminar flow condition. And by making use of this, we also concluded that average velocity is nothing but half of the maximum velocity at the center line. Shear stress, wall shear stress has this relation. From that wall shear stress, I find the loss for laminar flow conditions, and from Darcy-Weisbach relation and the relation that we had obtained, we concluded that F friction factor for laminar flows is equal to 64 divided by Reynolds number. This is a very, very important result. So let me just repeat it again. If you are solving for friction loss in a pipeline, the first thing that we need to do is to define the state of flow. How do we make that clear, whether you have laminar or turbulent flow? What we do is we calculate Reynolds number. After you find your Reynolds number, depending on the magnitude, the value of that Reynolds number, we conclude whether the flow is laminar or turbulent. How? If your Reynolds number is less than 2000, less or equal to 2000, we call it laminar flow. If it is greater than or equal to 4000, we call it turbulent flow. In between, it is named as transition flow, as we know. So if you have laminar flow, if your Reynolds number is less or equal to 2000, then we know that the friction factor, Darcy-Weisbach friction factor, is equal to 64 divided by that Reynolds number. You can calculate this F directly and use it in the equation, Darcy-Weisbach equation, to solve for the friction loss that occurs between those two sections, which are L apart, with a diameter given and with the velocity hat that you have. I hope it is clear for that laminar flow calculations.